Good morning, students. Today we will discuss a new chapter which is about sound wave. This is the first part of sound wave, which is about sound production. Sound waves are the most common example of longitudinal waves. They travel through any material medium with a speed that depends on the properties of the medium. As the waves travel through air, the elements of air vibrate to produce changes in density and pressure along the direction of motion of the wave. The amplitude of sound will determine the loudness of sound. We can see here the higher the amplitude, the louder the sound, and the lower the amplitude, the quieter the sound. While the frequency of sound will determine the pitch of sound. We can see here this is the wave shape for a low-pitched sound, and this is the wave shape for a high-pitched sound. This has lower frequency than this one. So the lower the frequency, the lower the pitch of sound. Sound waves are divided into three categories that cover different frequency ranges. Audible waves lie within the range of sensitivity of the human ear. They can be generated in a variety of ways, such as by musical instruments, human voices, or loudspeakers. The frequency range is between 20 Hz and 20,000 Hz. Infrasonic waves have frequencies below the audible range, less than 20 Hz. Elephants can use infrasonic waves to communicate with each other, even when separated by many kilometers. Ultrasonic waves have frequencies about the audible range. It is more than 20,000 Hz. You may have used a silent whistle to retrieve your dog. Is it really silent? The ultrasonic sound it emits is easily heard by dogs, although humans cannot detect it at all. Ultrasonic waves are also used in medical imaging, or we usually call that USG. Now we will speak about sound production. Sound can be produced in many ways by many different instruments and devices. A vibrating string or air column can both make interesting music, and it is good to understand the physics between both. Let us see this demonstration. This is a wave generator. It generates certain frequency, and we can see that using this wave generator, we can set the interval the frequency increases at. This is when the frequency is 13.7 Hz. This is the first harmonic. This is the second harmonic, when the frequency is 27 Hz. When the frequency is increased, then this is the third harmonic. You can see the number of notes and anti-notes are different for different frequencies of sound. So for this vibrating string, a Malthus experiment using this apparatus, we have a vibrator here or a frequency generator, and there is a certain load here which will cause tension to the string, and then when we generate the frequency, there will be standing wave here. In both ends, there will be nodes, just like what we have seen in the previous demonstration. Malthus experiment shows that the speed of sound in the string will be equal to the square root of the tension of the string divided by mu. What is this mu? This mu is the mass per unit length of the string. So this mu is constant. When we change the length, the mass will also change, so that the ratio between mass and length will always be constant. And then because mass is rho times volume divided by L, and volume can be written down as A, cross-sectional area multiplied by the length. We can cross the length out, so mu will also be equal to rho times A. So we can change this equation of V into the square root of F over rho times A. And now we will see the equations of a vibrating string. We have this string of length L, and this is when the first harmonic is generated. The first harmonic is also called the fundamental note. We call this F0. F0 is when this L is equal to a half lambda. There will be only 2 nodes and 1 antinodes. So lambda is equal to 2L, and we know that frequency is equal to V over lambda. That's why we have F0 equals V over 2L. The second harmonic, or the first overtone, it happens when this L is equal to 1 lambda. We call this F1. L equals 1 lambda. There will be 2 antinodes and 3 nodes. And then we can say that F1 is equal to V over L, or to V over 2L. The next will be the second overtone. It will happen when the length of the string forms 1.5 lambda. This is called the second overtone, or the third harmonic. We call this F2. The L is 3 over 2 lambda. So F2 is equal to V over 2 over 3L. Then we have F2 equals 3V over 2L. And we can generalize this as F0 to F1 to F2 will have the ratio of V over 2L divided by 2V over 2L divided by 3V over 2L, and that will make a ratio of 1 to 2 to 3. So if you want to find F1, we'll just have to multiply 2 by the fundamental note, or the first harmonic. That will be 2V over 2L. When you want to have F2, F2 is the third harmonic, or the second overtone. We'll just have to multiply 3 by F0, 3V over 2L. Yeah, that is for vibrating string. We will see the example problem now. A string of length 1 meter is given a force of 100 newtons. When the string is vibrated at frequency of 500 Hz, 10 antinodes are formed along it. I have drawn here 10 antinodes. So it consists of 1, 2, 3, 4, 5 lambdas. Remember that 1 lambda consists of 2 loops. So 5 lambda equals 1 meter. So the lambda will be 1 over 5 meter. We want to calculate the mass of the string. From the frequency and the lambda, we can find the velocity, the speed of sound in the string, which is lambda multiplied by f, or equals 100 meter per second. And we have one more equation, v equals the square root of f over mass over L, or the mu. So v is 100, f is 100 newtons, L is 1 meter. We can calculate m by squaring both sides. We'll get 10,000 equals 100 over m. So m is equal to 1 over 100 kilograms, or equal to 10 grams. The second example. In Meld's experiment, a tuning fork of frequency 365 Hz is used as the vibrating source. The string is given a load of 96 grams. I calculated it in newtons, so divide by 1000 and multiply by 10 meter per second squared. It equals to 0.96 newtons. And the distance between two adjacent nodes is 4 centimeters. I draw this two adjacent nodes, 4 centimeters, it is a half lambda, 4 centimeters. Calculate the speed of the wave in the string. So we can find lambda, which is equal to 8 centimeters, then V equals lambda multiplied by F. Lambda is 8 centimeters, F is 365, then we can find V, 2920 in the unit of centimeter per second. Question B, the tension should be given to the string so that the distance between two adjacent nodes now becomes 5 centimeters. Now the lambda is no longer 8 centimeters, it becomes 10 centimeters. Then V now will be 10 multiplied by 365, it will be equal to 3650 centimeter per second. So we know that V is proportional to the square root of F, or tension. So we can write this equation, V1 over V2 equals the square root of F1 over F2. Then V1 is 2920, V2 is 3650, but we can make that 4 over 5, or 8 over 10, because we can cross F out. It is equal to the square root of 0.96 over F2. So we can find F2, which is 1.5 newtons. We want now to find the weight of 1 centimeters of the string, given G equals 980 centimeter per second squared. The equation of V is equal to the square root of F over M over L. And then V is 36.50 in meter per second, equals 1.5 over M over 1. And we can calculate M now. It is 0.001126 kilograms. So if we want to find the weight, then use mass times G. The mass is 0.001126, and the G is 9.8 meter per second square, so I got 0.011 newtons. Many instruments make music by causing a vibration to a column of air in a resonator. These are usually called wind instruments. Examples of these are flutes, recorders, or saxophones. They are either open at both ends or closed at one end and open at the other. The pitch of the sound is a function of the frequency. Now we will see for the closed end air column. When we have a closed end air column, then it will be open at one end and closed at the other end. At the closed end, there will be node, and at the open end, there will be antinode. So if we see here that the fundamental note or the first harmonic will occur when the length L of the tube is 1/4 of lambda. So F0 will happen when L is equal to 1/4 lambda. So lambda is equal to 4L. That's why when we have F equals V over lambda, then F0 will be equal to V over 4L. The lambda is 4L. And so the first overtone or the second harmonic or F1, we'll just have to add one loop here. So now we have 3/4 lambda in 1L. So L is equal to 3/4 lambda. So lambda is 4 over 3L. That's why F1 is equal to V over 4 over 3L. Then F1 is equal to 3V over 4L. The next overtone, the second overtone or the third harmonic, will happen when we add one more loop here. So now we have 1 lambda plus 1/4 lambda. So F2 will happen when L is equal to 5 over 4 lambda, or lambda is equal to 4 over 5L. Then F2 will be equal to 5 phi over 4L. If you see in the book, the symbol of the fundamental is F1 in the book. We will use this one. The fundamental note or the first harmonic will always be F0. The first overtone, the second harmonic will be F1, and so on. Okay, now we will generalize the equation. So F0, the comparison of F0, F1, and F2 will be equal to phi over 4L over 3V over 4L over 5V over 4L, or it is 1 to 3 to 5. So if you want to find F2, that will be 5 multiplied by F0. So it will be 5V over 4L. If you want to find F3, then F3 after this, the third overtone, it will be 7 multiplied by F0. So it will be 7V over 4L. That is for the closed end air column. Now for the open end air column, when it is a open end air column, both are open. So in both ends, there will be antinodes. So we can see here that 1L is a half lambda for the fundamental note or the first harmonic. This is called F0. L equals a half lambda, and lambda equals 2L. F equals phi over lambda, then F0 is equal to phi over 2L. This is similar to the vibrating string. Only that for a vibrating string, both ends are nodes. Here in the open end air column, both ends are antinodes. So the second harmonic or the first overtone will happen when we add one loop here. So F1 is when L equals lambda, then F1 equals phi over L. The second overtone or the third harmonic or F2 will happen when we add one more loop. So now there will be 3 over 2 lambda in 1L. So this is 1 lambda plus a half lambda there. So F2 is equal to 3V over 2L. So we can generalize this exactly the same as the vibrating string. F0 to F1 to F2 will be 1 to 2 to 3. So when we want to find F2, then it will be 3 multiplied by phi over 2L. Yeah. Now we can summarize this. We can see it in the table. It is written in your book on page 172. We have vibrating string here as the sound production, the source of sound. For vibrating string, phi will be equal to the square root of F over mu. Mu is mass over L or rho times A. As I told you, it is constant. And we have two more source of sound, open air tubes and closed air tubes. This phi equals F times lambda can be applied for those two. So the fundamental note for the vibrating string and the open air tubes will be the same. F0 equals phi over 2L. But for closed air tube, it will be phi over 4L, as I have explained before. So the ratio of F0, F1, and F2 here for the vibrating string and the open air tube, it will be 1 to 2 to 3. For the closed air tube, it will be 1 to 3 to 5. And then the number of nodes at nth frequency. For the vibrating string, it will be n plus 2. For example, for the fundamental note, then the number of nodes for the vibrating string will be 0 plus 2. there will be two nodes. But for the open air tubes and the closed air tubes, for the fundamental node, the number of nodes will be only 1. The number of antinodes will be n plus 1 for the vibrating string, and the closed air tubes. For the open air tubes will be n plus 2. If you don't want to memorize this, you can just draw them. Yeah, here n is 0, 1, 2, 3, and so on. The fundamental node where n is equal to 0. Now we will see the example problem. An open air tube can produce second harmonic of frequency 1500 Hz. The speed of sound in air is 340 meters per second. Calculate the length of the tube. The second harmonic is equal to F1. F1 is 1500 and V is 340 meters per second. For an open air tube like this, I draw this. This is F1. See, we have 1, 2, 3 antinodes and 2 nodes. And here L is equal to lambda. So F1 is equal to V over L from the equations that we have derived. So 1500 is equal to 340 divided by L. So L is 0.227 meters or 22.7 centimeters. When the same tube is made a closed air tube, what is the frequency of the first harmonic? Now we have a closed air tube, and the fundamental node or the first harmonic equals the fundamental node will occur when the formation will is like this. We have one node and one antinode, and here L is equal to 1/4 lambda, so lambda is equal to 4L. And then for the first harmonic, F0 is V over 4L. The length is 0.227. So the frequency of the first harmonic will be 375 Hz. Number 2, an open air tube can produce fundamental node of frequency 170 Hz. The length of the open air tube is the same as the length of a closed air tube. Yeah. What is the frequency of the first harmonic produced by the closed air tube when the speed of sound is 340 meters per second? So here from the fundamental node of the open air tube, we can see that the equation that we have is frequency equals V over 2L. So because the frequency is given 170 and the V is given, we know now the length of the open air tube. And the length of the open air tube is the same as the length of a closed air tube. The length is 1 meter. So for the closed air tube, to find the first harmonic, which is F0, we have the equation of V over 4L. V is given 340 divided by 4 multiplied by the length 1 meter. So the frequency of the first harmonic will be 85 Hz. So now what you have to do is to understand the lesson from this video, and then you try to do the example problems in your physics book, page 170 and page 172. That's all. All of them have been discussed. So please try to do it. And then the more problems in your book, page 177, number 1 until number 5, let's just make it your homework for tomorrow. So you can do it tomorrow. All you have to submit now is the example problems in your book. Please try to understand. If you have anything that you don't understand and you want to ask, you can contact me, in these numbers. Okay, I hope this video is useful, and thank you for your attention. Goodbye.